Hello, my name is Hasanat Hasan, and for the summer 2023 Emerson program, I chose to work with Dr. Nicola Lanata on a project aimed to improve quantum embedding methods. However, it was modified because the original idea was not realizable due to a theorem. With the original goal of working on quantum embedding methods, thankfully the project was smoothly transitioned to performing benchmark calculations for a newly developed density matrix renormalization group code, or DMRG code, while maintaining the core of the original project. The presentation will follow this structure in which the first focus is introducing the problem of predicting the behavior of electrons in quantum matter and the role that quantum embedding methods play. Then, I will provide a brief overview of the many prerequisite concepts and the mathematical techniques required in order to contribute and ultimately complete the project. And lastly, I discuss the results of the task and the next steps in progressing the work and how my training benefits me and in my potential in pursuing physics. Let's begin with some relevant background information. Modeling the behavior of quantum matter has been a long-standing problem in physics, and progress in it brings benefits to many fields such as materials science, engineering, medicine, and many more. However, performing calculations of quantum matter and considering the many interactions pose a great computational challenge. Thus, quantum embedding methods like the Ghost-Godzwiller approximation, or GGA, were developed to tackle this endeavor. The GGA method is an algorithm that iteratively computes the ground state of an embedding Hamiltonian with bath degrees of freedom, and greater baths yield greater accuracy. To the right, we can see a visual representation of the algorithmic structure of the GGA code, in which it takes an impurity in a lattice and couples it to bath degrees of freedom. This system of impurity in baths is what is known as the embedding Hamiltonian, and the GGA iteratively computes the ground state of the embedding Hamiltonian for greater and greater number of bath degrees of freedom. However, the computational cost associated with calculating the ground state grows exponentially with the number of baths, hence the demand for efficient ways to calculate the ground state. Recently, a DMRG code was developed by the Center for Computational Quantum Physics, or CCQ, called ForkTPS, and it shows great promise in efficiently calculating the ground state of an embedding Hamiltonian for large numbers of baths. Because of the potential that the ForkTPS code presents, the opportunity arises to combine the ForkTPS code with the GGA. Then we would reduce the computational cost of calculating the ground state of the embedding Hamiltonians for the GGA method, thereby increasing its efficiency. Before we proceed with combining the two, it is necessary to check its capabilities with other known methods to make a real assessment of its potential. Hence, the task of this project became to perform benchmark calculations comparing the accuracy and efficiency with previously established methods like quanti, that is based on a brute force method of exact diagonalization. Embarking on this task requires many prerequisite physics and mathematics, requiring a strong grasp in the second quantization formalism, in which we use the fermionic algebra and Fock space to describe quantum mechanics in terms of creation and annihilation operators acting on quantum states. Using only the pieces of information I was provided, I was given many exercises along the way to prove many key theoretical results that serve as a basis for more advanced theory, like deriving the matrix representation of operators, and especially using the Fermi function to calculate the expectation values of a one-body Hamiltonian. Using the prerequisites and theoretical backing to make practical calculations, I eventually reached the key topic being embedding Hamiltonians, and the main computational tools related to them, that being the Fermi function and quanti. For embedding Hamiltonians, when it comes to the limiting case of no Hubbard interaction, we can use the Fermi function as a means to efficiently and analytically solve for the ground state energy and create the ground state density matrix. The ground state density matrix is a mathematical object that yields useful information for us. The second tool, quanti, is a software package specialized for solving quantum mechanics problems such as calculating the ground state energy, the ground state density matrix, and many more. For this project, its greatest use lies in calculating the ground state by using iterative algorithms like the Langsauce algorithm to solve for the ground state. Thus, quanti is a very broadly useful and reliable tool for simulations of small quantum systems. After learning both, I eventually gained the skill and understanding to then recreate the results of a published scientific paper. In this paper, the researchers calculated the energies of the first excited states of the following Hubbard Hamiltonian that describes a one-dimensional superconducting ring lattice which is coupled to an external electromagnetic field accounted for by the omega parameter. With the Hamiltonian in the paper, The researchers calculated the first few excited state energies as a function of the omega parameter for a few different cases of the Hubbard interaction, the first case being no interaction and the rest being different interaction strengths. The strategy was to first use the Fermi function to calculate the ground state energies for the no interaction case and then replicate with quanti. After I was able to replicate the ground state energy with quanti, I was confident in my ability and was able to replicate the following Hubbard interaction case of u equals -2, where we can see a strong resemblance between the two plots. The right side is the original and the left side is the quanti replicated calculations. After I was able to obtain consistent benchmark calculations for the paper, I was able to move on to the main project of performing benchmark calculations for the following embedding Hamiltonian, where the first term is the on-site impurity energy term, where the epsilon sub a is a constant for the on-site energy. The second term is the Hubbard interaction term that accounts for lattice vibrations and Coulomb repulsion and attraction. The U constant represents the interaction strength. The third term is the bath term that accounts for the interaction between the baths, where nu is the number of bath sites. And the fourth term is the impurity bath hybridization that accounts for the interaction between the impurity and the bath sites. Given a choice of values for the coefficients for the terms in the Hamiltonian, I was tasked to calculate the ground state expectation values of the double occupancy of the impurity site, where the double occupancy can be thought of as encoding the probability of two electrons occupying two spin states at the same time in the impurity site. And I was to do this for bats nu equal to 3, 5, 7, 9, and 11. I was also required to calculate the ground state density matrix for each value of nu, where the ground state density matrix is a matrix whose entries encode the expectation values given the ground state of an embedding Hamiltonian. Now, because I had already completed the task of replicating the results of a paper, the main task of performing benchmark calculations of this embedding Hamiltonian was a very natural extension, with only a few more complications for adjusting the variables for each term. For this embedding Hamiltonian, the interaction strength was non-zero, so the Fermi function for exact analytical solutions did not apply. Hence, the benchmark calculations were all performed using quanti. With quanti, the strategy was to create the Hamiltonian, then solve for the ground state. And with the ground state, we can then calculate the expectation values of the double occupancy, and we can calculate the ground state density matrix for each value of the baths nu and for different coefficients. I was able to perform the calculations and present the following figures for the expectation values of the double occupancy of the impurity site for the case of u equals 1, where the expectation value of the double occupancy is represented by the n-hat symbols. Taking a close look on the plot of the left, we can see that as the number of baths increase, the probability of finding both spin states occupied in the impurity decreases. Supporting the plot is the table on the right that contains the exact expectation values of the double occupancy of the impurity for the baths. This data will therefore be used as a comparison for the Folk TPS code. And note that the density matrices are not shown because the dimension or size of the density matrix grows linearly with the number of baths. With the obtained dataset in hand, the next stride in research is to employ the Fork TPS code. This endeavor aims to replicate the benchmark embedding Hamiltonian, followed by the computation of the expectation values of the double occupancy. These results will then be compared to those derived from the quantity calculations. Furthermore, the potential of Fork TPS to handle significantly larger sets of bath sites offers the promising outcome of improving the effectiveness of the GGA algorithm to ultimately further progress in many fields, such as material science, medicine, engineering, and so many more. However, the following phase, marked by the use of the Fork TPS, lies beyond the scope of the present project. Time constraints and technical complexities have prevented me from progressing to the next stage. Regrettably, the replication of Quanti's data using Fork TPS code could not be realized within the reach of this project. Reflecting upon the extensive journey undertaken in this project, the second quantization formalism, the comprehension of fermionic algebra, and the intricate calculations of the expectation values with both the Fermi function and Quanti, it becomes evident that the most logical path forward is to persist. While this project may conclude here, the amassed knowledge drives me to continue exploring the intricate realms of condensed matter theory. Thank you all so much for this opportunity.